And so far tonight, we have a couple people that have, but we have a message from Randy, who's actually away, and we also have Reg giving a talk. Is there anything else? And also, actually, David Lee has some stuff to speak about. Before we get going, is there anybody who also wants to speak about anything tonight, or show us any pictures or anything? Okay. Sounds like we're good to go. Why don't I kick?
I can find them.
Oh, you might. Okay, good. Well, let's start off. Randy had recorded a message. He wasn't able to come. And I will do like Reg, and I will try to share the video of Randy, and I'll also do my best to make the sound appear. So let's see how this goes.
Hello, my Astro friends. Sorry I can't come to Astro Cafe tonight, but I still have a couple of things that I'd like to present today. So here we go. I'm going to say share screen and start presentation. So lots and lots of really great pictures of the Jupiter-Venus conjunction this week. I just choose one that's been in our emails. This is from Martin. Look at that. You see the Galilean moons on Jupiter. This was done, I think, on Wednesday last week. Well done. Anyway, lots of great pictures. And then this APOD, Astronomy Picture of the Day, came out on Wednesday, showing the progression day by day from February 21 to the actual conjunction on March 2nd in India. It's kind of cool that you see the crescent moon wandering through the picture in the second frame. Beautiful. It's even my non-astro friends were remarking on it. Everybody that cared to talk to me about it was saying how beautiful it was. So what's happening? Well, yes, of course, it isn't that Jupiter and Venus are close to each other. It's that Venus is coming around, moving away from the sun. It's moving up in the sky. Well, Jupiter is kind of going up, but the Earth is coming around closer to the sun. So Jupiter is actually dropping down towards the sun, and they crossed last Tuesday when it was cloudy. Anyway, this happens often, but some are better conjunctions than other. And I found this really good website that talked about it. Not a website, an article that was referred to in my Facebook feed. So the big thing is, first of all, you have the inclinations of the disk of rotation of Venus, which is maybe about 3 degrees, and Jupiter, which is about 1 degree. And so you can actually have it up to 4 degrees different when they get past each other. And second, it depends how close they are to the sun. So, half the time, Venus is behind the sun or in front of the sun, or at least pretty close. And so you don't get a good view of them because it's during the daytime when they're crossing. The Venus can be up to 47 degrees away from the sun, but that is not for very much time each month. So somebody did this very clever diagram, this guy Hartigan from Rice University. So let's take a look at what we have. First of all, we have the oh dear, I've got this thing, degrees above the horizon at sunset. Okay, so that's when Jupiter and Venus are in conjunction, how far are they from the sunset? And when it's in these kind of low angles, you're not going to see very much because it's going to be daytime. On the other hand, the other axis here is the separation. So how close do they get? And that's because of the different planes of rotation. And it's not very, it's nice, but it's not very impressive when it's over a degree. But it's really when it's under half a degree, when it's like less than the moon apart, that's when we really like it. So the on March 1st this year, it was just around half a degree. Now, there are going to be other times that they're much closer. I don't know which one that is, but 2016, 2056, they're going to be really close. That's about 0.1 degree. That's going to be super, but very close to the sun. That's where it was last year in 2022, but take a look. This is a good one, way up at like 45 degrees and what, about 0.2 degrees. So all you have to do is wait another 13 years, okay? And then we're going to have a really, really good close conjunction high in the sky. So that's something to hold your breath for. What's the next one that's going to happen soon? I saw that, oh heavens, which one was it? There we go, 2025. A couple of years, they'll be about 0.9 degrees apart, high in the sky. That one, we can hold our breath till then. Anyway, it was really good, and I love the pictures that people have been posting. I certainly watched it. I didn't get any, well, I took some pictures, but they were lousy compared to the ones you guys were showing. Anyway, one more slide. Annual general meeting. It's happening next week. Won't be the same link as our normal Astro Cafe link, but Chris is emailing it around, has emailed it around, or Jill emailed it around. Please come. We need 25 people. The most important thing in terms of legalities is we're going to have Deb's financial report, and Reg is going to run our election. And please come. We need 25 people. There's not going to be a social event this time. Oh yeah, there's going to be the awards. You gotta see the awards. But a couple of weeks after that, on the 27th, I checked out the Moon Underwater Pub. It looks really very good, and I love the name. So unless something else changes, please plan on coming for a social dinner at the Moon Underwater on Bay Street. It will be on Monday, March 27th. See you then. Bye-bye.
Well, there we go. I assume that you guys could hear that. Otherwise, it would have been somebody screaming at me. Okay, excellent. Reg, why don't you fire up your presentation?
This is going to be a technological high wire act. I don't know what we're doing here. So I've got a video that I'm going to present, and we're going to possibly have to do something. But in the meantime, I'll just start it off. Is this TikTok? Who is that guy? Okay. All right.
Okay, you will need to.
They're turned off.
We just need to turn them on when you get to the video.
I think we need to do more than that.
We'll work it out. We'll work it out. Bear with us.
Hello, good people. This is part 2 of the case of the close encounter, the hunt for the culprit. And a recap of our last episode, which occurred on January 9th, 2.6 million years ago. Just a sec here. I've got a whole pile of things.
You can just look up there if you like.
Thumbnails obscured my screen. Just a sec. 2.6 million years ago, the Earth passed through the plume of the supernova. And now, traces of the isotope iron-60 were detected in the ocean floor sediments. The relationship between iron-60 and the supernova is explained here. And apparently we cannot share YouTube videos on the web, so there's a link to it. And this supernova coincided with the Pliocene-Pleistocene boundary extinction. And this might be a coincidence, but at any rate, there it is. And that is associated with the reduction of large marine species. And could nearby supernovae cause climate change, which is the real reason I'm interested in this topic, but it's a topic for another night. So, okay, so 2.6 million years ago, Earth was a victim of a supernova hit and run. Where is the culprit today? Let us consult some forensic astronomers. This is hard to do because supernovas don't leave skid marks. So the hints are provided in a breakthrough paper by Catherine Zucker and a group that published it about a year ago on January 2022. And it's called Star Formation Near the Sun is Driven by Expansion of the Local Bubble. And this is the paper if one wants to get access to it. And one thing about this paper, it's not very long itself, but it has tremendous results. And it's deceptive. The paper is actually built on a scaffolding of a whole pile of other important papers. And it really is an excellent example of how important it is to collaborate and how we have to specialize now. As astronomical knowledge is accumulating faster than one can digest it. So that's a big problem for us. But speaking on that, astronomy is no longer quaint. Okay, this is a cloudy night in Bath, and William Herschel is inside polishing his mirror while his sister Caroline is very happy because she doesn't have to stand by an open window and record his measurements that he yells at her in a flickering candle flame. So it's the best of time for her. But this kind of brings me to the question, I don't think I'd want my next door neighbor yelling numbers to somebody in the middle of the night. So I don't know how popular he was in the community.
He had a big estate.
Did he? Well, apparently, I don't know. At any rate, astronomy is no longer quaint. And we're now in the era of big science. And there's no bigger, better example of that than the Gaia spacecraft. It's an astronomical big science. And the papers by Zucker and others are all examine the recent motherlode of data captured by Gaia, and it's inspired an astronomical gold rush. And this might be one of the biggest things as we look back in decades to come about the Gaia data set is infiltrating and impacting all sorts of astronomical areas. But it would appear that Gaia has hijacked this presentation. And in 2016, I wrote an article for Sky News about the Gaia spacecraft in I think it was a November issue. And the reason I did is that 2 months beforehand, the first data release was done. And there was this picture that I showed at the time. It was a video, but that's quite a few years now. And I don't think people will mind if I show it again. And some people have joined the club since then. So if you've seen it before, please forgive me, and we'll carry on from there. And I don't know how this is going to work. So we're going to try and
Does it have sound?
I just play it.
Yeah.
We'll see what happens.
One billion stars. This is the number that the European Space Agency mission Gaia will reach, mapping each star over 70 times to nail down their position, movement, and characteristics. In the end, we will hold in our hands the most precise three-dimensional map of our galaxy. But how exactly will the mission measure such a vast number of stars? With its two telescopes, Gaia looks at two patches of the sky at the same time. A series of mirrors guides the light to the camera, the most powerful camera ever flown in space, with 106 CCDs and almost 1 billion pixels. When light from the first telescope reaches the camera, the first column of CCDs in the star mapper, on the right, selects the stars that will be followed and measured. When light from the second telescope reaches the camera, the second column of CCDs in the star mapper selects the stars that will be measured. As Gaia scans the sky, the light from both telescopes moves across the camera. But not all data need to be read out and stored. The onboard computer assigns a small patch or window around each star. As the image of the star moves across a row of CCDs in the camera, the star's position and brightness in this small patch on each CCD are recorded. This method is an optimization to deal with the enormous amount of data collected by Gaia's camera. Only a few dozen pixels on each CCD contain information about the star, so only those are read out and the corresponding data stored. The largest section on Gaia's camera is the astrometric field. As the image of a star moves across its 9 columns, each CCD measures the star's position and brightness. Then the starlight passes through two special prisms that direct different wavelengths to the 2 columns of CCDs in the photometer. This provides information about the star's temperature, size, and chemical composition. Light from a subset of stars also reaches the radial velocity spectrometer, 12 CCDs that are used to measure how fast stars are moving with respect to us. For each star, the information collected by all CCDs is compressed into a data packet and stored in the computers on board Gaia. This process is repeated over and over for each star. An average of 2 million stars are measured every hour, generating a total of about 50 gigabytes of data every day. This is equivalent to more than 10 DVDs worth of information every day. The data packets for each star are transmitted to Earth, where they are received at the European Space Agency's ground stations. The data are processed and analyzed by astronomers, who use them to investigate the three-dimensional distribution and physical characteristics of stars. When all this is done, Gaia will have created the most precise three-dimensional map of our galaxy, the Milky Way.
Turn my speakers off. And we'll go to the next slide. Okay, thank you for bearing out with me there. Seems like it worked. These are the prisms that were mentioned in the video, and they're important because they were used in this study that Catherine Zucker and group did. And so they're photometric. And here is just a second, Dave, you raised your hand?
Well, I just wanted to mention that we use the data from Gaia to calibrate our backyard astronomy pictures. That's all I wanted to say.
Thanks very much, Dave. Dave is stealing my thunder. At any rate, this is a picture.
Sorry, Reg.
This is a picture of the color of the sky from their Gaia's early data release number 3, done in December 2020. And each one of these things here is it's not a photograph. Each one of these things is a pixel. In the early data release 3, there's about 1.5 billion measurements of brightness in blue light, red light, and white light, and about the same number of detailed measurements of parallax and proper motions. So it's a huge game changer for the astronomical community and created a tsunami of data. So the data release 3, the complete data release 3 occurred in June 2022, and it had the same amount of data that they had with the previous release, but it also had, they had gone through and very carefully quality controlled the data, and then they identified a bunch of objects as well, and a whole types of different variable stars and this sort of thing. They classified over 10 million variable stars, and we have over 33 million radio velocities in the database. And this is the data set. So it was originally to end in 2019, but it's been extended to 2025 when the gas that controls the orientation of the satellite runs out. That's going to be 11 years of data, and it's going to have over 150 complete surveys of the sky. And it measures it about once every 27 days, the stars get measured. And so we have precise observations of the stellar positions. And this is the important thing. It's all done above the Earth's atmosphere. So we don't have any problems with turbulence. We don't have any problems with refraction or anything like that, which is a good thing. The accuracy of the proper motions will continue to improve as more data is captured as the stars continue to move across the sky. The radial velocity of the brighter stars is going to probably improve as well. Unprecedented accuracy of the parallax and stellar distances is just going to be great. The 3D positions of stars plus 3D motions of the stars is available. Precise measurements of magnitude in white, blue, and red are there. And there's an extensive quality control and reduction of the data. There's over 400 astronomers probably working on the side of the desk doing the quality control of this stuff at the European Space Agency. The Gaia data release 4 is scheduled for 2025, and at that time there will be 66 months of data. And then there's going to be a subsequent one about 2030 when data release 5 is coming in. So the big question here, so we got a lot of data. How are these people using it? First of all, they can use this to determine the density of dust between stars by measuring the interstellar extinction. I'll talk to you more about that in a minute. They define the extent of the local bubble, and I'll talk about that as well, and estimate the thickness of the shell. And they refine the membership distance and motion of open clusters. And then they trace back the position of these clusters over the last 16 million years. And they put all these things together, and it greatly improves insight into the location and rate of star production in the local neighborhood. So one thing that we should talk about is interstellar extinction. And this diagram here shows an incident star that passes through a cloud and then hits the telescope. When it goes through the cloud, some of the light is absorbed and some of it is scattered. And the blue light is scattered more than the red light. And we call this interstellar reddening, and it's not like a redshift. Instead, it's more the effect you get from a sunset. The observed or apparent magnitude of the star M is related to the absolute Gaia magnitude M sub G. The Gaia provides an accurate measure of both the apparent magnitude M and the distance to the star in parsecs. And so this is the equation that we have here, but there's one problem with it. If we have dust, it will make the star appear dimmer. And the way the magnitude scale works is the higher the number, the dimmer the star. So we have to add a number to that. And it's kind of like a fudge factor. It's called interstellar extinction A. So the equation here just has that added to it. And so that'll increase the magnitude, making it look dimmer. From the interstellar extinction, you can estimate the optical depth and the density of the dust, which is an amazing achievement. The extinction is challenging to determine because it requires one to know the intrinsic or true luminosity of the star. And the Gaia photometric colors can help do that. And I got a whole pile of stuff here I'm not going to go through. But the Gaia has two prisms. The GBP is the blue prism magnitude, and similarly for the red prism. And if we subtract the two, we get a thing called the color index, which is similar to a spectral classification. You know that the type of star classification that the women in the glass universe did with the various letters. And the other thing they do is they can take the color index for an intrinsic or the star that has not been dimmed by dust and subtract it from the observed one, and you get a thing called the color excess. And the intrinsic values are modeled on theoretical spectral classification. The color excess is caused by interstellar dust and is related to the interstellar extinction A and the density of the dust. Now, because we have, in this case, 27 million stars, it's brought statisticians out of the woodwork, and they're having a field day with all of this stuff. And they've got all of these exotic statistical techniques that I will not explain to you because I couldn't understand any of them. So there you go. But I will show you kind of a rudimentary thing. I took 30,000 stars. The royal we, somebody took 30,000 stars from Gaia within the 163 light years, assuming there's minimal interstellar extinction. And we plotted them on a chart called the Hertzsprung-Russell diagram. And down here we have the color index. So blue hotter areas are over here, red cooler areas are over here. And in the first time they did the Hertzsprung-Russell diagram, they had star classifications that were used by the glass universe people. On this column here, we have the absolute magnitude of the star, and 0 means that it's really bright, a lot of luminosity, and down here at 15 means it's very dim. So basically what we can have there, remember this thing here is called the color index. And if we just do an example, let's say we have a star, its magnitude is 5, and we go over to this thing which is called the main sequence on the Hertzsprung-Russell diagram. The color should be around down here around 1, but the actual measurement might be GB minus RP might show it here. And that's a way to indicate that there's interstellar reddening there. And as I said, the papers use a much more sophisticated way of doing it. And I'm going to quit while I'm ahead there. So how do they map the 3D interstellar dust? Imagine you've got a pea shooter or a straw with a field of view of 6 arc minutes. It's a pretty small thing. For each star in this field of view, the 6 arc minute field of view, Gaia has got the distance, intensity, color index, and 3D motion for each star in that little tiny area. Along this sight line, the density of interstellar dust between two subsequent stars can be calculated. And you might have 2 or 3 stars in that pea shooter. You might have 25. At any rate, it can go all the way out there and calculate how much dust is between each of those stars. And the accuracy is around 2 parsecs, which is around 6 light years distance accuracy at this stage. Now imagine there was a similar straw for every direction in the celestial sphere. We can now create a 3D map and the interstellar dust cloud for the entire sphere surrounding Gaia. So in this particular case, the paper that they used used 27 million stars, and they calculated the interstellar dust map for within about 10,000 light years of the sun. And the mapping was done by a team in France, and this is the name of their study that they used. So now this is an example of what the local bubble dust map looks like, and I might show it later if time permits. But the local bubble itself is a cavity of low density, high temperature plasma surrounded by a shell of cold neutral gas and dust. The dust density, the wall thickness, and the velocity of all of these things allows a person to calculate the momentum of the entire local bubble. And they use that value to figure out how many supernovae it would take to create the momentum of this shell. And the answer is about 15. So it's quite an ingenious thing. The other thing that they do is trace back of star clusters. Now, members of an open cluster are close together and they move in a similar direction and speed. And the uniform motions of the Gaia early data release 3 set were used to refine the membership in the clusters in the local neighborhood. They ignored any gravitational effects from neighboring star fields. And they used the main gravitational effect from the galactic gravitational potential of the Milky Way as a model of the core gravitational field, the disk, and the halo. And they didn't have to write any code for this because in the collaboration, they have a Python galactic toolkit called Galpy. And so they could go in there and do this, and they could extrapolate backwards to estimate the positions of these clusters millions of years ago. And they assumed that the initial supernova was in the Scorpius-Centaurus OB association. What's an OB association? Those are the really bright white stars that burn fuel very quickly and can go through their fuel in a couple of million years, and they die young. So they, somewhat like rock stars. And they estimated around 15 supernova at a rate of about 1 per million years would generate the momentum that would have inflated and created the local bubble. And the shock wave from the supernova would act like a snowplow and pile up all of the dust in the area, and the shock wave would help create star forming regions on the perimeter of the local bubble. And here's an example of the supernova remnant. This is taken from Hubble. Not all supernovas are so obedient and send out stuff in such a beautiful way. So what I'm going to do now is get out of the presentation and show you a model that they produced. And okay, so what we've got here is a view of our area 16 million years ago. And at that time in the upper Centaurus region, there was a star cluster forming. And as we go down, about 14 million years ago, they had a supernova go off and it created a bubble. And as we go along in time, the bubble expands, and some of these star clusters here associated with the Taurus, a molecular cloud network. And you can see these things sweeping out. And as a shock wave of this bubble gets into the area where these stars are, or star clusters, it would stimulate star formation and maybe create a couple of OB stars that would create a supernova. And at the meantime here, this little dot here is the sun, the motion of the sun. The sun's not in the bubble at the time. As we step forward a bit, you can see it expand. It gets a bit closer, and about 5 million years ago, the sun passed the threshold of the local bubble and moved into the interior of it. You can see how it comes. And if you get closer, you can see that the bubble is getting very close to one of the cluster lines there. And around 2 million years ago, there's an intersection with that. And this is what it looks like today, with the sun in the center of this. And I've got another beautiful interactive thing I can show later if there's interest in that. It shows what all the features around the local bubble are today, but I'll leave that for now. And I'll go back to our presentation. And so the location of the culprit, the tracebacks of the forensic analysis estimate that the sun entered the local bubble 5 million years ago. Around 2 million years ago, the tracebacks for the Taurus C9 cluster intersected with the path of the sun. It is possible that the supernova associated with this cluster produced the iron 60 plume that the Earth traversed 2.6 million years ago. But personally, I think that the evidence is really weak. And if I was on the jury, I don't think I would accept it. So the evidence is insufficient to press charges, and the Taurus C9 cluster will be classified as a prime suspect. We'll leave it at that. Case closed. And this is a diagram of the C9 cluster here. And where in the world is that? If we go to a star map, the Auriga constellation is here, Aldebaran's there, Betelgeuse is here, and in the middle is this nondescript area called the Taurus molecular cloud. And that's a star forming region. So that basically where it is. So if you look up in that sky, just remember that one time, 2.6 million years ago, we had a visitor that passed through our area, is in that area now. So the summary of the Zucker et al. Findings: nearly all the star-forming complexes in the solar vicinity lie on the surface of the local bubble. Their young stars show outward expansion, mainly perpendicular to the bubble surface. The tracebacks of these young star motions support a scenario where the origin of the local bubble was a burst of stellar birth and then death of a supernova taking place near the bubble center 14 million years ago. The expansion of the local bubble created by the supernovae swept up the ambient stellar medium into an extended shell. That has now fragmented and collapsed into the most prominent nearby molecular clouds. This provides robust observational support for the theory of supernova-driven star formation. So quite an amazing paper, and we didn't know any of this beforehand, and this gives proof and is really moving the field forward. But I'm not finished yet. There's a golden opportunity here for you folks. The Gaia Gold Rush has just begun. They'll be still collecting data for the next, say 7-8 years. And the data is freely available for all. The AstroPython software routines are also free. It's a great opportunity for you to search for nuggets and do your own citizen science project. And you don't need a gold pan. Just load Python onto your computer. It's free. And teach yourself Python and you're ready to go. This website down here is an invitation for you how to download the data. It tells you alerts when there's things like interesting things, photometric things discovered, and they want people to do follow-up measurements. And similarly with objects in the follow-up network for the solar system, where there are asteroids discovered, it might be something that you give some consideration to. At any rate, and if you wanted to read all about it in Sky News, when it was breaking news 6 or 7 years ago, here's the link. And I didn't mention this. There is a thing called the Radcliffe Wave, and I just wanted to ask Brock, how is our time? Did I go back and show somebody the features?
Our time, I think we're okay. There's only David Lee has a few SIG announcements, but did you want a few more minutes?
Yeah, okay, I'm sorry. I just go back to this other model, because one of the real strengths that Catherine Zucker had was that the visualization software they use. Like this is a visualization software, 3D software. You can see this is the boundary of the local bubble. They can also turn on dust clouds that they also measured through this process. We have things like stellar clusters. These are the clusters that were used. These are the Taurus clusters. We also have a series of clusters in the Perseus. These are the Orion cluster. And we have clouds, skeletons that can be associated with these clusters. These are the molecular clouds. We have a feature called the Perseus Taurus bubble. And this is another bubble that showed up. And on one side of the bubble, we have the Taurus molecular cloud. On the other side of the bubble, we have the Perseus cloud. And actually, the collision of these two help energize the Taurus molecular cloud, which is the closest molecular cloud to the sun. The sun's position is here. What they had in the past was a thing called the Gould's Belt, which was actually thought to be a circle that had a whole pile of these bright OB stars on it, and they thought it was in a ring that was somewhat inclined to the galactic plane. But actually, what they discovered, Zucker and group found in January 2020, that there's a thing called the Radcliffe Wave, and it is a thing that is like this. And the galactic plane, it starts up and then goes down here. And it's amazing. And there was another feature called the split. The split is a line that goes from our local arm to the what is the Perseus arm out here. And these two features are enough to explain where the OB concentrations are. And the Gould's Belt is no more. It is just kind of a myth, and we should have a funeral for it sometime, but we'll let that go. At any rate, it is really quite fascinating the way you can find out and look and see the insight that this gives. And it is just wonderful. So I'm just going to get out of that and go back to this. Well, if you want to know more about the Radcliffe Wave, there's an absolutely fabulous interview by a person called Dr. Becky, who does these interviews with people and talks on various astronomical projects. She's from Oxford University. She actually interviewed the 3 primary authors of this paper, and they told her how they figured out this Radcliffe Wave. Radcliffe is named after Radcliffe Hall in Harvard, and that's where a lot of these people work. And so one guy called up his another one of the people, said, "I got something really important to tell you." She had a house full of people at the time. She said, "Well, I better come over." He says, "I've got Indian food. You can have Indian food." And they said, "You better come bring Catherine too." So all 3 of them got around there and they showed this stuff. And at first they thought this thing was wrong. It was crazy. And then they looked at it more and more, and Catherine got in and did her visualization software, and they could see this sinusoidal wave in that, and they're blown away. But this gives you kind of a very colorful description of how scientific discoveries happen. So I encourage you to give that a YouTube video ago. The other thing is that the January issue of Sky Telescope, Brian Van Rudo has a beautiful article called "Riding the Radcliffe Wave." And the neat thing about that is all of the beautiful objects in the sky, the North American Nebula, all your favorites on this thing. So he's got a lovely table there to show all these deep sky objects that are all fairly close by. And if you've got that magazine, I would check it out. And with that, I'm going to surrender the screen and be back to you. Thanks very much.
I think Dave Payne has a question.
Yeah, sorry about spoiling your. But so the gold and silver and uranium and all that stuff that we find in Earth, maybe the start of the sun. Do we know anything about the supernova that created that, or is that
No.
too far back?
Oh yeah, this is the whole thing. See, I was really interested a couple of years ago when I found out about this business of possibly a nearby supernova, to go back and tiddly figure out the mass of all of the local stars and that, and work my way backwards, put Newton's laws of motion in reverse, and go back and extrapolate backwards and find the location of this. And it probably wouldn't have worked because it's just too noisy. But the beauty with clusters is they've got momentum. They're like a motorcycle gang. They'll stick together for a while before they get in quarrels and they leave the organization. So they're going to hang around for long enough that they've got the momentum to stay intact. So by focusing on these clusters and then working backwards, it was quite an ingenious way to find out what was going on. And so that's why they were used in that case.
Thanks.
Great talk, Reg.
Thank you.
David Lee. Oh, he's just clapping. Perfect. Any other questions for Reg before we pass it over to David? Sounds like you're up, David.
Okay, well, we've got a busy week this week. Starting tomorrow, we have our beginner's SIG, and we've been kind of working on sort of naming standards. So tomorrow, we're going to talk a little bit about comets. Since we've been viewing comets recently, we'll talk about how comets are named. So there's kind of like the old school, very original way, and then what the IAU has defined. So we'll talk a little bit about that. I'm hoping maybe Jill might want to talk about any future outings for the group. Also, I think Marjie had a question about the retrograde motion of planets. So Lauri and I are going to try to tackle that tomorrow night as well. Now, I might be a little bit late. I have a class group meeting, but Lauri said that she would be there to welcome people and chat with people until I arrive. So this Thursday is Citizen Science, and thank you, Reg, for a great talk that sort of promotes the concept of citizen science. I'm hoping that periodically through Astro Cafe, I'll introduce you to different types of citizen science projects. There really are kind of like two main categories. There are some that are really, really easy to do, and they only require a little bit of commitment and a little bit of time to do. And then there are other ones which are a little bit more long-term. So at the Thursday meeting, I'll maybe try to get some samples of each type, and then also tell you what the toolkit looks like the toolkit for doing more elaborate citizen science. So that involves things like learning a little bit, remembering all your statistics, learning Python, maybe Jupyter notebooks. So a lot of those kind of tools are readily available. They're actually free. So I can sort of introduce you to those if you wish. So those are the two SIGs for this week. I haven't seen anybody sign up for Citizen Science SIG yet, so please let me know if you're interested. Otherwise, it'll just be me. So I'm sure you won't want that. So yeah, so let me know if you're interested, and I will set up the list. Thank you.
Thanks, Dave. Now, I think David Payne mentioned that he might have a picture or two.
Just have to hear my screen.
Ah,
There, that's what.
nice.
So I happen to be at the right place at the right time. My wife is very supportive of my astronomy work, but she wouldn't bring my passport to dinner. So I have to just use my iPhone to take this shot. This was the closest that I saw Venus to Jupiter, and they happen to be sort of parallel to the horizon. And you know, using the pinky test, I found that that was less than half a degree apart. Could have been half a degree or something. Using my pinky test, less than half a degree. And the interesting, so I sat there and looked at, well, why don't they directly overlap? Because of course the ecliptic isn't perfect. The planets aren't exactly on the ecliptic. They're all a little bit on. And so I looked up and found out that the planet, it's kind of old data, because it said the planet that was most off was Pluto, which was 17 degrees off of the ecliptic. So it would be a rare circumstance to see Pluto exactly on top of the planet. And just thought I'd let you guess what the second most furthest away from exactly on the ecliptic planet is. And give you a second to guess. You can shout the answer if you know. The second most distant planet from the ecliptic is actually Mercury. And it is 7 degrees off the ecliptic. And so its plane of orbit is 7 degrees off the ecliptic, which maybe explains why it's such a rarity to see Mercury transit. Other than that, these two planets, Jupiter, are less than a degree off the ideal ecliptic, at least at this stage.
So David, were the people around you asking you what those were, or did they know?
A few were asking me what I was taking a picture of, but I also encountered other people taking a picture of the phone.
Very nice.
Mhm.
Thanks. Eric?
Well, maybe I'll have to share a picture too. I do actually have a picture of a bubble, so that it kind of goes with what Reg was talking about. It's formed by a different thing though, but I'll share it anyway. So where am I here? Why can't I see it? Hold on. Okay. Can you guys see the bubble?
Yes.
This is
Very nice.
a shot I got a week or so ago. It's Jones Emberson 1. I had never seen this one before, but I saw an amazing picture taken on a 1 meter telescope that I won't show because it puts mine to shame. But some guys in France did an amazing shot of this. There's got to be about a gazillion galaxies in the background. Mine, you can only make out 1 or 2, but it's a nice planetary nebula. It's not from a supernova, but it's similar in that it's a star near the end of its life and an expansion of gas. I don't know if that's a white dwarf in the center, but there is a little white dot in the center, so I'm just going to go with that being a white dwarf. I don't know, but it was it's a nice it's actually a really faint target, and I was quite happy with. I didn't have much exposure time, so I will probably, next clear night I get, I'll probably point my scope at it again because I'd really like to get a bit more detail on it. But
Brock, scale wise, how big is it relative to, let's say, M57, the Ring Nebula?
it's bigger than the Ring Nebula visually, like its apparent size in the sky. This is pretty much the full frame of the camera. The Ring Nebula is probably half that diameter with that same magnification. So
Okay.
but I'd never heard anything about it. But if you do go to Astrobin and check out, it was one of the top shots, but it's one of those pictures that you could stare at for an hour. Like you just keep zooming in and panning around, and it's maybe I'll quickly see if I can find it and I'll paste a link in the chat. But that one that those guys in France took, it's just galaxies, even inside the center, looking through it into the background, there's galaxies. It's such an amazing, it almost looks like something you would have got from Hubble or JWST. There's so many galaxies in it. So anyhow,
So what makes you say it's not a planetary nebula? It's a planetary nebula.
no, it is a planetary nebula. It's just not, sorry, I might have misspoke. It's not a supernova remnant.
Right.
Right. I might have just been.
And now you have to try for the other Jones one, which
What's
is
that?
Jones 1.
Okay.
Without the Emberson.
Where's that one?
It's in Pegasus.
And is it also a planetary nebula?
I think so. Yeah.
Okay.
It kind of looks, it's very similar in shape.
Okay. I'll try to get it. I assume you've seen it.
Yes, both of them.
Okay. Are they pretty faint? You need the 20 or your big 24-inch?
No, a 12-inch will get them.
Okay. No, I have a challenge. What about my 8-inch Dob? Probably be a bit tough.
Not from where you live.
Yeah, well, that's
That was your Celestron, was it not, Rob? If
Yeah.
you got that?
Yeah.
Not-
9 1/4, but not visually, I think is what Bill's referring to.
Yeah, that's right.
Yeah. Cool. Anybody else have some new? Oh, did I see Marjie? Go for it, Marjie.
Hello. I can now really appreciate Bill Weir's attitude towards looking at the sky because thanks to Jill, I am now participating in the Explore the Universe program. I have 10 objects checked off and recorded, which has been a lot of fun. And I have had several incidences where I can actually see things from my balcony. So I go outside and I go, oh, I can see that. Okay, I'll go get my book. I get my book and it's clouded over. Second, I do something else. I look outside, I can see it again. I get my book, I go outside, it's clouded over. So just that whole, I'm going to put my book closer to the door, I think. I can now really appreciate, being like, seize the moment. Thank you, Bill.
Marjie, the trick is you go out when it's cloudy and you wait.
Ah,
That sounds cold.
Yeah, I think the best example of delayed observing notes being made was when Dorothy was at the eclipse in Oregon. And she did a complete sketch a couple of hours after the event. So you could do that. Give it a try. See how your memory's like. Your visual memory.
I've got an image I'd like to try and show if I could.
Yes, please go ahead.
Ooh. I've got two screens turned on here.
You can pick the screen.
Click the screen?
You can pick the screen. Your
Okay.
second one will be beside your main screen in the choices, if that's where you want to go.
No, I want to go here to desktop number 1.
Yep. So just pick the leftmost one.
And then you have to click the share button.
Yep.
Second.
Yes.
What's this open preferences?
No.
Nope.
The green share button, select the screen you want, and then press this share button after that. 3-step operation.
It says I've got a. Oh, I see. I'm not going to make it here. Just a second. I'll turn the other screen off. How's that? There we go.
You got it.
We can see your screen.
Okay, can you see that?
Yeah.
Now, I was watching TV and this was a couple of days before they were really close together, but I saw this sky and I just thought I'd give it a try. And it's off my deck and you can see the Capitol Dome here. And these are the red antenna lights over on the west shore. And there's lots of light here. So it's kind of a light polluted subject, but I'm surprised how much you can see. If you use your imagination, you can see the Terminator on the moon up here, and the bright things show up. And that's handheld. I think it ends up being about a 5 5 or 6 second exposure at a really high ISO. So anyways, for what it's worth, there's a lot of lens aberration too. As you can see, the buildings are sort of leaning into the center, but I mean, that could all be corrected if need be. But
those particular planets, Doug, were quite bright, like even visually. So
Yeah.
they were very bright on the frames anyways.
Yeah, I should have actually reduced the exposure a little bit, and I probably would have gotten a cleaner shot. But
it's nice.
It was just while there was a commercial on the TV. But and it was from outside, and the wind was really blowing. I couldn't stand and hold the camera steady. I had to lean up against the building. But I'm surprised the detail in the foreground.
Actually, the iPhone, the later iPhones, they'll correlate an image even if you're waving the phone around. It's amazing.
Oh, is that right?
It'll put up a lot of motion.
Yeah.
Maybe not for stars though.
Yeah, it's a fairly wide field as well. That's saving you as well, because the wider the field is, the more forgiving it is.
Yeah, well, the little Olympus cameras, I've got a small Olympus camera, and it's got a total of about 5 stops of motion reduction between the camera and the lens, so that helps too.
Yeah, it's
anyways,
good.
I just thought I'd show that for interest.
You know, I think some of the best shots are snapshots. They're just to remember the moment, right?
Well, it records the moment, and I like it when there's something around it to get some
context.
Context to what you're looking at. But I'm amazed how many people, including my wife, walked back and forth by that same window and didn't see it. But as soon as I pointed out, it's, wow, is that ever neat? You know. So that was my outreach for that evening.
Yeah, very nice.
One Galileo moment.
Yes.
I got a couple of pictures I could show, Brock. Are you hearing us?
Yes. Yeah.
Yes, I just carry on.
Yeah.
Not seeing you though, Ron.
He's off frame. Trust us, he's here.
I had some notes for all this stuff, but I left them at home, of course, so. This is the Horsehead and Flame Nebula.
Ken, this is the one that you said that you had so much trouble with. What was the magic that restored the image for you?
There's several processes in weighted batch processing in Pixon site that I went through the masters at Pixon site and got some good information out of them, and they led me down the right path. I tried the HDR composition in it, whereas in the weighted batch processing you can do much of that. When you do that, run that script, so that seemed to help out.
That's good.
And I also did it in black and white, which I think shows a bit more definition to it, a bit more contrast. other two I was gonna show you would be the Orion Nebula. And it kind of interested me in the trapezium. It's so bright in there, so it's hard to get the rest of the Orion Nebula to come out. So that kind of bothered me a bit. So I tried to get the trapezium in another picture, which I did here. I'll run through here. I'll play it again.
You can see them there.
Yeah, that's the trapezium in there.
Mhm.
I think that's about 1.5 light years across. There's a couple of binary stars in there. I think there's a total of 8 stars in the trapezium. And they're pretty new stars. I read somewhere that they're about 300,000 years old. Should be able to get that up. Anyway, I was kind of real happy I was able to get that out. I haven't totally processed that picture yet, but that will come later on down the road.
That's fantastic, Ron.
Yeah, nicely done.
Thank you.
So what equipment are you using?
I've got an ASCAR 107 PHQ scope, so 107, and it's 750 millimeters, and ZWO 2600 MC, and that's on Skywalker's EQ6 mount.
And a special camera of some sort?
The camera's a 2600.
Okay.
ASI 2600.
Nicely done.
Just click the webcam.
Yeah, no, I was gonna try and blow it up.
Oh,
But I keep on getting this.
Yeah,
they're
I
trying
want
keep
to,
things
does
in
it?
one
No,
spot,
yeah.
so.
Mhm.
Just get out of it.
Thanks for sharing, Ken.
Okay, you're welcome.
Brock, I have a photograph that is not too exciting in the world of astrophotography, but very exciting for me.
Okay.
Okay. Well, that wasn't it. All right.
I was going to ask where you took that one.
Yeah,
Okay,
that was
share-
a
This is where we go.
On a spaceship.
Okay, share screen. Maybe if I speak out loud, it'll help. Click on desktop 1. Well, the thing is, it's not on desktop 1. It's down here. La 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 la. See if that helps. Ah, there we go. Oh, that doesn't help. All right. Share screen. I can do this. Click on desktop 1. And press share. Well, that's just going to give me you guys. Hello.
No,
There you go.
we can see it.
Okay.
Confusing, isn't it?
Oh, there it is. Yahoo! Where'd it go?
That's a great shot.
Yeah, very good shot.
Oh, goody, you can see it. That was February 23rd.
Is that the same night as Doug?
Yeah,
Off my
looks
balcony.
like it.
I think it
Yeah.
is, yeah.
Everything's in line.
There we go.
What did you take that with, Margie?
My Lumix camera.
Good exposure on the moon. You can
Mhm.
see the crescent.
Mhm.
Nice.
Very nice. Thanks.
Okay, have I stopped sharing now?
You have
Excellent.
successful share. Okay, it's 20 after 8. Is there anyone else has any business or talks or anything to share? Sounding quiet out there.
Lauri, you don't have any announcements from the Hill?
No, I don't think so just right now.
Okay,
We're waiting. The posts have come in, the guardrails have come in, they are on the hill, but they are not up yet. So we still have not got a we still haven't got a specific date for when it will be back open again. But we do have an open house coming up on the 25th and 26th of March. And that is cross fingers that every
Oh, you accidentally muted.
go. We've still got 3 weeks to go. And it will be Saturday night from about 6 to 9 or so that will be open. And then Sunday afternoon from about 11 till 3 that we're going to be open. And there won't be any tickets or anything. We'll just have people coming up to the hill and saying hi and getting back up again. And it's part of the there's other things that are open for kind of an open house. It's not quite the be a tourist in your own hometown, because that's not going on this year, but the same kind of idea. Like, I think things in the area will be all open, so hopefully people might come by and help out. And then the other thing that I just wanted to am I still muted? No. Okay.
No.
The RASC General Assembly is going to be from the 5th of May until the 7th of May, virtually again, online. And on the Friday night, we have been invited to have a tour of the DAO in conjunction with a tour of the DDO, which is in Toronto and is the sister telescope. And so we're going to be on from between 7 and 8 o'clock at night. Now we know that it's going to be just at the end of the sun is just going to be going down. So we won't be doing any nighttime work, but we might be able to put up the solar telescope. Excuse me. And Dan has said that he would help out with some of the plasket, oh, excuse me, some of the plasket tour and some pictures. And we'll just invite people in from across Canada to see what we're doing. And we would love to have 6 or 7 people from both the FDAO and the RASC help out with that program on the Friday night. So if you're interested in helping out with that, we'd love to have you up and be hosts for the rest of Canada that will be on the virtual program. The other thing you talked about this, David, about starting the citizen science, and one thing that we do have going on at the GA are poster sessions that people with citizen science projects that they're working on, or either starting or have finished off anything that they'd like to present, is we'd love to be able to have a poster put on at the sessions kind of in the evening, and then you can be at your poster virtually, and people can come and talk to you about what you're doing.
well,
And
well,
so we want to have
might be nice to summarize our Sky Brightness project.
Yeah. It would be a perfect place to do it, is to put something in, and the call for projects will be April the 1st. So, and then it'll be a poster. Anyway, lots of things going on. So we'll just keep going. Thank you.
Okay.
One comment
Lauri.
about the GA. The annual general meeting will not be held in conjunction with the GA. So the GA is basically just the fun stuff. And the national AGM will take place in late June.
I believe it's the 25th.
That's right.
I think it's a Sunday. It's a Sunday, if I'm correct.
That's right. Yeah.
Yeah. So just put that on your, and it's virtual again. So same thing. So that's, and just the business of the organization will be at that meeting. So.
Okay. Thanks, Lauri. Unless we have anyone else, I think we could probably wrap. I think we're excellent. Okay.
So just a reminder of the AGM next week.
Yes, remember the
And
AGM.
that's online only. So
Okay.
no nobody being here.
Okay, we'll see you all then.
Thanks, Brooke.
Have a good night, everyone.
Right.